For this demonstration, we will concentrate on glued contact with an example of an airframe model. The component meshes can come from different sources that may or may not have a common nodal boundary. We will quickly assemble these components using glued contact and make an assessment of the performance. We can also integrate the local modeling within the primary master assembly. The focus of this demonstration is on ease of use and how one can remove traditional mundane tasks from their assembly modeling process while maintaining accuracy on stiffness and loads transfer. I have a Patran 2010 session open, and on the screen you can see the airframe model. Patran 2010 is our latest release and has some new features for improved usability. A new skin approach has been introduced to improve user efficiency by providing a fresh appearance to the menus that is consistent with the Windows and Office application. The Windows version of Patran adopts a skin approach whereby users can choose the interface appearance they would like depending on their preference. So on this screen you can see I have the ribbon Office 2007 ribbons where I can traverse between geometry ribbon, materials and properties, loads and boundary conditions, and meshing, and it reduces the number of clicks that I have to make to get to a particular action. You can also customize your Patran environment to fit your application needs. In this new interface, the standard toolbar has been replaced by the quick access bar. So for example, if I'm a frequent user of let's say creating this isometric view, I can quickly add it to my quick access bar, and once I travel to different ribbons, this quick access bar will provide access to this isometric view through this quick access bar. Coming back to the model, the airframe panel has some ribs on it, and we have two primary types of contact. One is the edge-to-edge contact between the refined section of the shell as well as the coarse mesh, and also the 2D edge contact between the boundaries of the window and the coarse shell. The other type of the contact is the face-to-face contact, and let me zoom in here. Let me zoom in here, and you can see we essentially have a mid-surface of two shells, and if these were 3D parts, they would be sitting on top of each other. So we need to pay attention to the curvature because the curved panel is flatter around curvature, and the ribs have a more discretized refinement. So we will need to play with the curvature, which I will demonstrate as we build this contact bodies. For the sake of this demonstration, I have already imposed the boundary conditions, and let's take a look at those boundary conditions here for a second. So I'm going to plot markers on the two boundary conditions. The pinned displacement is essentially constraining the displacement of the top and bottom edge, and have applied an internal pressure. An internal pressure is applied on the outside surface, including the window. So we will start by creating the contact pairs, and we will create a contact deformable body, and to speed this process I will first post only the ribs, and then I'm going to create a 2D deformable body called 2D ribs, and select the application region, finite elements, and select all the elements to create these 2D ribs. And once I say apply, you will notice that these 2D ribs appear on the existing sets. I will repeat this process for first the panels and the window. And same procedure, I'm going to create a deformable body, call it panels fine, and I'm going to select the application region, to say add, I'm going to say apply. The next step is to create the course shells, and for this I need to post the course shells, and I'm going to select the application region, and I'm going to say apply. So now I have created these 3 contact bodies, and to verify that these have been connected properly, I'm going to say plot contours for all of these 3 bodies, but before that I will post all of the groups. And I'm going to refresh the graphics and plot the contours of these 3 contact bodies. So you'll notice that the 3 colors have been identified. The green is the 2D ribs, the yellow is the fine panels as well as the window, and the blue is the shell's course. So I now have created contact bodies, and as already said, we already have created the loads and boundary conditions, the displacement and pressure. So now we are ready to create our contact table. I'll verify that my solution type is 101, which is the linear static, and I'm going to go into subcases, select my default subcase, and go to subcase parameters to create the contact table. I will deactivate all and between the panels fine and 2D rib, I'll double click to create a glued contact. T here stands for touching contact, and G stands for glued contact. We can specify the distance tolerance, and I'm going to select automatic and retain moment in this case. I will repeat this process for shell's course and 2D ribs, and create this same distance tolerance as well as the moment. Between the shell's course and the panel's fine, we will change the tolerance. Before I submit my solution, I want to select the default subcase, and if your pattern is connected to the MD Nastran solver, this solution took about 15 seconds, and I have accessed my results, and I'm going to plot my results here. The solution took about 15 seconds, and now I can come in and plot the displacements, and as you can see, we have the displacements essentially plotted for this contact problem, and what I can do is modify the way it looks and make it shaded and remove the undeformed. So as you can see, we can plot the deformation contour. The next step is to also plot this without the fringe, and we'll deactivate the fringe so that it looks better, and we can focus on a certain piece here and see that although we can see a crack here, if it was a a real gap, this would have been blown up by quite a bit. So in a sense, this concludes our demonstration for glute contact, and you can see how quickly we have been able to assemble this model, and without the need to make it nodally congruent, and while maintaining accuracy and stiffness along with it.